Okay, in the last segment, we talked about various graphs and the information that we can get from the graphs, including energy of reactants, energy of products, activation energies when we're catalyzed, forward enthalpies, reverse enthalpies. These are a wealth of information, okay? Now, we're saying that enthalpy is the main driver of Gibbs free energy, so we're going to largely look at enthalpy to simplify the thermodynamics. We're going to begin this section with, well, what happens if we still can't get a reaction that's favorable as written and we still want it to go forward anyway? We will have to do some reaction coupling. So we're on page 7 of the lecture notes, and let's say we want to boil some water. We're going to have to go from liquid water to water vapor, which means we're going to have to put some heat into it. Well, this is never going to go forward unless we can find a heat source. So we're going to couple it, for example, to CH4, which we're going to combust to make CO2 plus H2O, and we're going to create heat when we do that. And indeed, when we light a Bunsen burner, okay, our Bunsen burner uses methane gas and we create heat. This heat will then drive this reaction forward. And this is what reaction coupling looks like. Okay, so will the reaction couplings below yield a spontaneous reaction? Why or why not? Well, remember what we're looking for is a delta H that is negative. Okay, so on this example, remember our delta H is going to be synonymous for our purposes with delta G. So A going to B plus C is negative 10. DE yielding F is positive 8. So we're going to show them coupled like this. This one's negative 10, this one's positive 8. When we couple them, we add them together, and it's negative. Negative. So if that's negative, this reaction will be spontaneous as written. And that's what it says. When combined, the coupled reactions have a net negative delta G, so both reactions can occur spontaneously. So this is a favorable coupling. Okay? In this example, ATP yields ADP plus a phosphate. Many of you have seen this. If you haven't, don't worry. But the general reaction has a delta H of negative 7.3 kcals per mole. That means that this heat is given off. Well, where is this 7.3 kcals going to go? Well, it's going to be used to see if it's enough to drive this second reaction, E plus F yields G plus I. Well, when we add these together, we end up with positive 3.1 kcals per mole. This is positive. This is not spontaneous as written. It's kind of like saying, I need $10.40, but you have only $7.30 to give me. So this one is a no. This would not work unless both of these went backwards, in which case this one would yield 10.4 and this one would absorb 7.3. In this reaction, we're going to go the other way. ATP yields ADP plus 7.3 kcals per mole. And the fact that we are showing that this is coupled to creatine yielding phosphocreatine means that this one requires less than or equal to 7.3 kcals to make that reaction go forward. And you will see a lot of coupled reactions of this type in your next course for those of you who go and take some biochemistry. Page 8, equilibrium is defined as the rate of the forward equaling the rate of the reverse. So at equilibrium, only is germane to reactions that are reversible. And you want to know, does the reaction favor the forward or does the reaction favor the reverse? And we tend to draw these arrows like this, and we tend to think that they're equivalent, but they usually and typically are not. Well, you can figure this out by writing what I'm going to call a KEQ. Now, you can also see this as a KC or a KA or a KB or even a KW, but I'm going to use an umbrella term called a KEQ. All right? Now, we can quantitate a generic reaction that's reversible. A plus B yielding C plus D, the little a, the little b, the little c, the little d are our stoichiometric coefficients that we use to balance. And so our generic KEQ is the products raised to the stoichiometric coefficients divided by the reactants raised to the stoichiometric coefficients, where the square brackets are equal to molarity. Okay? Now there's a whole lot more to this story, but we're going to go with the broad generic idea of products raised to their stoichiometric coefficient divided by the reactants raised to their stoichiometric coefficient. Okay, so N2 plus 3H2 double arrow 2NH3, our KEQ will be the molar concentration of NH3 squared divided by N2 times H2 cubed. And that's our KEQ expression. Our HCN, our KEQ, which I'm really going to call a Ka because this is an acid, is going to equal H plus times Cn minus divided by HCN, and these are all molar concentrations. Okay? Page 9. H2 plus O2 yields H2O. Okay? So our KEQ in theory here would be H2O squared, assuming that's water vapor, H2 squared, O2 to the first. Now, how can you tell if these will go forward or backwards? Well, K means constant, which means it's something that you go and look up. Okay, you find these in a table somewhere. Okay, so we're seeing a lot of places where we go and look stuff up. A periodic table, an activity series, an electronegativity chart, a solubility table, some enthalpy data, some entropy data. We just go look stuff up. So let's say we look up this reaction and it has a KEQ of 1 times 10 to the minus 5th. Well, remember that negative powers of 10 means that that power of 10 goes into the denominator, which is the same as saying 1 over 100,000. Remember, the numerator is products, denominator is reactants, and so this is saying that the reactants are favored, which means that our equilibrium favors reactants and very little of it goes in the reverse. What if the KEQ is a positive power of 10? And so again, the positive power of 10 is in the numerator. This is products over reactants. And this is saying now that the products are favored. Sorry, I got distracted. I don't know if you can hear my cat meowing in the background. Okay, so I'm sorry. So reactants means that the A is favored and very little of it goes forward. On this one, the products are favored, which means very little of it goes backwards. Okay? So in general, what can you say if the KEQs are negative powers of 10? Negative powers of 10 mean reactants are favored. Reactants are favored. If we have a positive power of 10, that says products are favored. And so the question becomes, what happens if we want to change the direction that is naturally favored? And that will occur in the next segment when we look at Le Chatelier's principle.